Yes, my voice is audible.
Yes, sir, it's audible.
Oh, 1 minute. Now the PPT is visible.
No, sir, not yet.
No, sir.
Okay.
Now visible, sir. Bulk modulus.
Yeah. 1 minute. Yes, now PPT is visible.
Yes,
Yes, sir.
yes, sir.
Okay. Yeah, now PPT visible.
Yes, sir, visible.
Yes, sir.
Yeah, what is the title of the PPT? The slide number? What is the title of the slide?
Compound bars.
Yeah,
Compound
compound.
bars, sir.
Okay, thank you, ma. Okay. Yeah, last class we discussed about compound bars or statically indeterminate member. When we say it's a compound bar means the bar is made up of two or more materials. A member is made up of two or more materials, then that type of bar is called as a compound bars, right? Means that carries only axial loads. The bar is made up of two or more material, subject to an axial loads, then that type of bar is called as a compound bars. Example we have given here, RCC, cables, take a duster, okay, electrical wires, those are comes under some of the example for compound bars, right? Then how do you solve, how do you determine the stresses induced in the compound bars, deformation induced in the compound bar? By applying, one is a static force equilibrium equation, that is vector sum of all the forces acting on a body is equal to 0. Second one is the equation of elastic deformation, means whatever the deformation takes place by the compound bar, those compound bar is should be same, right? That is also called as compatibility equation, geometric relations. Another one is equation of elastic deformation. And also we know that what is a statically determinate member, indeterminate and redundancy problems. Then we solved a problem on compound bar, right? Then later we discussed about elastic constants. These are the constants which are express the elastic behavior of engineering material. Means when you apply a load up to elastic limit, how the material, engineering material behaves. What are the elastic behavior of that engineering material within the elastic limit, that tell by the constants called as elastic constants. There are four elastic constants depend upon the type of load acting on that engineering material. If the material is subjected to a tensile load, it may be axial load. Axial load may be tensile or compressed in nature. Then what type of modulus will come within the elastic limit is a modulus of elasticity or Young's modulus, that we represent as E. Suppose if the engineering material is subjected to a shear load, right? Shear load, then within the elastic limit, what f of modulus will come here? Shear modulus or modulus of rigidity. Why the rigidity term come here? The body will not undergo any deformation. It will change only the shape, right? That's why the term rigidity comes. Modulus is nothing but constant for rigidity. Now third one is if the engineering material is subjected to a three mutually perpendicular stresses of the same magnitude, means along the x direction we apply right hand thumb rule. Okay, thumb shows x axis, forefinger shows y axis, and middle finger shows z axis. If your component is subjected to three mutually perpendicular normal stresses of same magnitude, means along x axis sigma is acting, along y axis also sigma is acting, along z axis also sigma is acting, right? Then acting on your body. Those stresses are called as a spherical stress or bulk stress. Once the spherical stress occurred over the body, means what happens? It changes its volume. Equally, it changes its volume. Then we'll get volumetric strain. The ratio of spherical stress to the volumetric strain is called as a bulk modulus. See the how do you remember this elastic constant? First one, when a member is subjected to axial load within the elastic limit, what type of stress will get? Normal stress. The ratio of normal stress to the normal strain is called as Young's modulus. Instead of normal stress, if a shear stress acting on a body within the elastic limit, what is the elastic behavior here? That is shear modulus, that is the ratio of shear stress to the shear strain. Bulk modulus means a member is subject to three mutually perpendicular stresses of same in magnitude. That changes the volume, okay, within the elastic limit. Then the ratio of spherical stress to the volumetric strain is called as bulk modulus. And last one is elastic constant is as you apply an axial load tensile force on the body, the length increases, at the same time the lateral dimension decreases. How much lateral dimension decreases, that we express in terms of the deformation takes place along the length. That effect is called the Poisson's ratio. It is the ratio of lateral strain to the linear strain, and negative sign also we use because of the lateral dimension decreases as the length increases. Those things we'll discuss in the last class, right? And also you should remember for engineering material, some of the engineering materials, what should be the Young's modulus for the steel and aluminum, and Poisson's ratio for the engineering materials. If you have any doubt regarding the previous class, now you can ask the doubts. If you don't have, then I will continue the class. There's no doubt? Okay. Now today we are going to discuss about one more very important law. Already we know that Hooke's law, right? Now here the term comes here, generalized Hooke's law. Now the PPT is visible. Someone
Yes, yes, sir. Yes, sir. Yes.
A generalized Hooke's law. As you know that already Hooke's law means nothing but within the elastic limit of stress strain curve, the stress is linearly proportional to strain. In order to remove the proportionality, we need a constant. The constant is called as a proportionality constant, that you get Young's modulus, right? But here the term here, generalized Hooke's law. So why do you use this generalized Hooke's law, right? Now here earlier we consider only if you apply a load in only one direction, how the material behaves. Okay, but here if you consider a cube, see the sketch here, consider a cube. Actually cube is not there here. Now consider this is a cube of length, dimension A, height also A, and width also A. I think this is visible in camera.
Yes, yes, sir.
Okay. Now assume it is a cube. It's actually a chalk piece box. Assume it is a cube of length A, width also A, and the height also A. The dimension of the each side of the cube is A. The volume of the cube is A cube, right? Now if the cube is subjected to on three mutually direction, x-axis, y-axis, and z-axis, the stresses are acting. Along x-axis, what is stress acting here? Sigma. Suffix in which axis here acting here? X. That's why it's called as sigma x. The normal stress acting in x direction. Similarly, on y direction, the normal stress acting in y direction represented as sigma y, and normal stress acting in z direction is sigma z. Okay, so consider a body subjected to 3 mutual perpendicular stresses such as sigma x, sigma y, and sigma z, as shown in the figure. Now consider here cube. Along the x direction, sigma x is acting. This is a tensile stress acting along the x direction, and tensile stress acting along y direction, and tensile stress is acting along z direction. These are normal stresses. Their magnitude is maybe same, not be same, maybe change. It magnitude changes. Magnitude maybe varies here. Okay. Now what happens when a body is subjected to a 3 mutually perpendicular stresses of different in magnitude, such as sigma x, sigma y, and sigma z? What happens? The body undergoes change in dimension. Once change in dimension, then I want to determine what is the strain induced in that body along x-axis, y-axis, and z-axis. Then how to determine the strain induced along the strain induced in the body? Now we'll go for apply first one, Hooke's law, that is stress is directly proportional to strain, and second one we'll go for apply principle of superposition theorem. So why do you go for apply the Hooke's law? Means within the elastic means stress is linearly proportional to strain. Second one, a body subject to several loads here or several stresses here. Then I want to go for what is the net effect of the body, means net effect strain induced in the body, that is equal to sum of individual effects that is produced by a body by considering individual load or individual stress. That says the principle of superposition theorem. See that the generalized Hooke's law states that when a body is subjected to normal stresses along the coordinate axis, coordinates axes are OX, OY, and OZ. X, Y, Z are the coordinate axes. The strain along those directions can be found by using Hooke's law and superposition theorem. Right? Then how do you determine? First, I want to determine what will be the net strain or total strain induced along x-axis. Once you derive for this, similarly you go for derive what is the strain induced along y-axis, what is the strain is induced along z-axis, the net strain or total strain. Now, how do you determine the net strain induced in the body along x-axis? First, I'll consider x-axis. Now, it consists of 3 components. Now, consider a cube here. The cube is subject to a normal stress along x-axis, normal stress along y-axis, and normal stress along z-axis also. First, I want to determine what is the total strain induced along x-axis. If you want to determine total strain induced along x-axis, first I will consider see that what is the first I consider only sigma x acting along the x direction. If you consider only sigma x means stress acting along only in x direction, means what happens? The strain induced here along the length direction, right? Then I'll go for consider one more stress here. We're neglecting sigma y and sigma z for first case. For second case, I'll consider only that you can see here. First, in the second figure here, consider a cube. Only stress is acting along x direction. Sigma x is acting along x direction. We neglect the sigma y and sigma z. Now, how much strain is induced along the x-axis here? That is called the longitudinal strain along the x-axis. Longitudinal strain along x-axis due to what? Sigma x. Similarly, what is the strain induced along x-axis when you consider only sigma y? Means stress induced along y-axis. We neglect the sigma x and sigma z. Right? So what happens here when the normal stress induced along only y-axis, but our aim is to determine what is the strain induced in along x-axis. Means we are applying a stress along y-axis, positive y direction. At the same time, in the x-axis, what happens? It decreases the dimension. That is the lateral dimension. That is a lateral strain along x-axis due to sigma y. Right? Similarly, if you go for z direction, if you load a stress is applied in z direction, we neglect the sigma x and sigma y. What happens? Strain is induced. I want to determine strain along only x-axis. Means along x-axis, the lateral dimension decreases. Right? Lateral strain along x-axis due to sigma z. Then you apply the principle of superposition theorem. The net strain induced along x-axis is a sum of the longitudinal strain due to along x-axis due to sigma x plus lateral strain along x-axis due to sigma y plus the lateral strain along the x-axis due to sigma z. Now this is the what next strain induced along x-axis due to sigma x, sigma y, and sigma z. Then how to determine sigma x and sigma x longitudinal, sigma x lateral due to sigma y, and sigma x lateral due to sigma z? How do you determine all these three things? First, you take first one. Consider a cube is subject to only sigma x here. Now here the sigma x acting along the x direction. What happens? If you sigma x acting along only x direction means the strain also induced along x axis only, right? See that the sigma by applying a Hooke's law. What is Hooke's law here? The stress is directly proportional to strain. Here what type of stress acting here? The stress acting along x axis is directly proportional to the strain along x axis. This is what type of strain induced on the cube here? Longitudinal strain, because sigma x acting along x axis, the deformation also takes place along x axis. What type of deformation here? Longitudinal deformation. Change in length takes place with the original length. Then you get longitudinal strain. Then in order to remove the proportionality, we get a constant. That constant is what we call as Young's modulus. Now from this, our aim is to determine epsilon x longitudinal. Epsilon x longitudinal is equal to sigma x by E. This is the first term. Next, what is second term here? Lateral strain along x-axis due to sigma y. If the lateral strain along x-axis due to sigma y, I want to determine. Now here see the third sketch here. Same cube is subjected to what? Sigma y axis. Yeah. Now consider this third figure here. The same cube is subjected to sigma y. The stress is acting in y direction. But our aim is to determine what? What is the strain induced along x-axis? Now how do you determine? As you again apply the Hooke's law, the stresses in y direction is equal to Young's modulus into strain along the y direction. This is a longitudinal strain along y direction. Now we'll go for express epsilon y longitudinal in terms of lateral strain. How do you determine lateral strain and longitudinal strain? By applying one more elastic constant is called as Poisson ratio. As you know, the Poisson ratio is equal to the ratio of lateral strain to the longitudinal strain, and negative sign is indicated here because the lateral dimension is decreases. Now what is the lateral dimension here? Consider x-axis minus epsilon x lateral divided by epsilon y longitudinal, right? From this I want to substitute, I want to take the longitudinal strain along y-axis is equal to minus lateral strain along x-axis divided by Poisson ratio. Now substitute this value into this equation, sigma y equation. Then simplify it. Finally we'll get what is the lateral strain along x-axis is minus mu into sigma y by E. Now the next slide is visible. Now
Yes, sir.
next slide is visible.
Yes, sir.
Yeah. One is lateral strain along x-axis due to sigma z-axis. If the stresses induced along z-axis, what happens to strain along x-axis here? Again, the same simplification what we have done for the previous one, lateral strain along x-axis due to sigma y, same derivation. Finally, we will get what? Lateral strain along x-axis is equal to minus mu into sigma z by E. Now, what is the net strain along x-axis? Now, substitute all those values into the equation 1, that is net strain along x-axis is equal to sigma x by E minus mu into sigma y by E minus mu into sigma z by E. Now you should remember this equation. How do you remember this equation? See that you remember this x, y, z. These are the coordinate axes. So if I want to write the strain along x-axis, in that axis only the sigma, the positive sign will come and apply the Hooke's law, we'll get sigma x by E. What are the remaining two axes are? Remaining two axes, what happens? The dimension decreases, right? Those are the lateral dimension. That's why we'll get the minus n with respect to minus n along with the Poisson ratio will get. See that by taking x, y, z, if I want to write epsilon x is equal to sigma x by E minus mu times of sigma y by E minus mu times of sigma z by E. Similarly, directly we write, once you derive for only net strain along x-axis, similarly go for write what is the net strain along y-axis, epsilon y, and net strain along z-axis, epsilon z. How do you write epsilon y here? Again, you use the xyz axis. If you want to write epsilon y, that is strain induced along y-axis, means on that axis only the positive sign will come. As you know that stress is equal to E into Young's modulus. Sorry, Young's modulus into strain. From this, strain is equal to what? Stress by Young's modulus. Right? So along I want to write strain, net strain along y-axis is nothing but, right, other two coordinates are becomes a lateral dimension, minus mu into sigma x by E plus sigma y by E minus mu into sigma z by E. Similarly, write for third coordinate also. So now how you should remember this equation. This all three equations is called as a generalized Hooke's law. Now, how do you say this Hooke's law is right or wrong? As you know that for a tensile test, you are derived that the stress strain diagram. In the stress strain diagram, you know the Hooke's law. Only stress is acting along x-axis. What about stress and acting on y and z axis are 0, right? Just substitute here. Sigma y is 0, sigma z is 0, because no stresses are acting along the y and z direction for a tensile test specimen, or what we discussed in the stress strain diagram for a mild steel, low carbon steel. Now substitute sigma y and sigma z is 0. Now finally what we get? Epsilon x is equal to sigma x by E. That is what here the Hooke's law it is. Similarly go for in y direction also, in z direction also. Now this is a very important formula you should remember. Okay, this is generalized Hooke's law. The generalized Hooke's law says that, what is the generalized Hooke's law says that when a body is subjected to the three mutually perpendicular stresses, in order to determine the strain induced in that body by applying two laws. One is Hooke's law, another one is superposition theorem, principle of superposition theorem. Yes, I have understood this concept. Yes, any doubt regarding this? And also you should remember this value, this equation, generalized Hooke's law. How do you write this generalized Hooke's law? Using coordinate axis x, y, z. Okay. If you want to write strain along x-axis, on that axis only the positive sign will come and sigma x by E will come. Remaining terms here, negative sign and Poisson ratio will come. Come to the picture in the equation. Yeah. Now the next slide is visible.
Yes, sir.
Yes.
Yeah, the title of the slide.
Relation between elastic constant.
Yeah, thank you, Ma. Now the relationship between elastic constants. Now we have 4 elastic constants for an engineering material. Okay. Okay, mute yourself. There are 4 elastic constants for engineering material, such as one is Young's modulus, second one is shear modulus, third one is bulk modulus, and fourth one is Poisson ratio. First, we'll go for what is the relationship between. Usually for engineering material, we know only 2 elastic constants. One is Young's modulus, other one is Poisson ratio. Then how do you determine the remaining 2 elastic constants, such as shear modulus and bulk modulus? For that, we should have a relation between the shear modulus in terms of E and also bulk modulus in terms of E and mu. Okay. So for engineering material, if we just give only 2 elastic constants, for isotropic material, remaining 2 elastic constants you can easily determine by applying the mathematical formula. Then how do you know that? What is the formula? How do you know that? Then you'll go for again a derivation. For yours, derivation is not important here, but some previous year question paper they asked for the relationship also. Maybe the syllabus also change it is. We don't know whether it may be asked or no, will not ask the derivation. But you should know, at least you should know. So what is the relation between Young's modulus, shear modulus, bulk modulus and Poisson ratio? and minimum one questions you can expect, not only for exam point of view, no, for the semester. When you go for competitive exams, okay, after completion of your 4-year degree course, when you go for apply competitive exams, 1 or 2 questions will come from these relations. Okay. Yeah, the first relationship you are taking here, relationship between Young's modulus and shear modulus or rigidity modulus, that is E and G. For that, what we will do, again we'll consider a plane lamina. Consider a plane lamina, consider this a plane lamina of A, B, C, D. All sides of the lamina. Lamina is nothing but it is a thin sheet, okay, a square lamina it is. All sides are equal, means see that here in the sketch, AB is equal to BC, BC is equal to CD, CD is equal to AD. All sides are equal. Consider a square lamina, okay, of equal sides. AB is equal to BC is equal to CD is equal to DA. Now one side of the lamina, the bottom side AD is a fixed one. Now the AD is fixed. Now we will go for apply a load. What type of load here? Shear load, shear force on the BC. Once you apply shear force on the BC, what happens? The square lamina become ABCD become, AD will not changes its position, B and BC will changes. From B it will changes to B dash, C will changes to C dash. Now you can see the A, B dash, C dash, D. That square lamina become what? It become a rhombus or it become a parallelogram, right? Now what happens here? At the same time, see that the CD line and C dash D, you can see that this is called the shear strain, means change in shape it takes place here, gamma it is, right? Now consider a square lamina of AB, CD. When a shear force is applied on the BC surface, now it is changes square lamina, it changes to a rhombus. Now where is the deformation takes place here? The deformation takes place is, change in dimension takes place in where here? See the diagonal AC. Now earlier diagonal AC, now if your shear load is acting on the shear force acting on the BC surface, now AC become what? AC dash. Now the dimension is same here. AC is equal to AC dash. No, the change in dimension takes place, means it increases its diagonal, right? Now the dimension changes takes place only in along the diagonal, right? And what will be the angle between C dash, C and after that, once it increases the length AC to AC dash, from the point C, draw a line which is perpendicular to AC dash. Draw a line which is perpendicular to AC dash. Now this angle here, C dash PC, this is 90 degree, CPA, this is also a 90 degree. But what about C dash CP? That angle is how much here? 45 degree. Remember that. This is a right angle triangle. That angle C dash CP is 45 degree. See that C dash CP is 45 degree. This is what is the theory portion here. Now consider a square lamina ABCD of unit thickness with its face AD is fixed rigidly and subjected to a shear force F on its face BC. As shown in the figure, the body takes new shape A, B dash, C dash, D after application of a shear force F. Now draw a diagonal AC dash, AC dash and draw a perpendicular line from C to AC dash. Okay, now meet at the point is called as a P. Then we have AC is equal to AP. And what is the C dash CP? That angle is how much? 45 degree. Now where is the strain? The change in dimension takes place. The change in dimension takes place only along AC, means diagonal. AC become AC dash. See that, right? Now once whenever the change in dimension takes place, then we go for determine strain induced in that diagonal. What is the general formula for strain? Strain is nothing but change in dimension to the original dimension. What is the change in dimension? Final dimension minus initial dimension divided by initial dimension. See that the diagonal AC is subjected to a normal strain epsilon AC, that is equal to Change in dimension nothing but final dimension minus initial dimension. That is the change in dimension to the initial dimension. FD stands for final dimension. ID stands for initial dimension. Okay, strain is nothing but what? Change in dimension to the original dimension. Change in dimension nothing but final dimension minus initial dimension or original dimension. Yeah, now next slide is visible.
Yes, sir. Yes, sir.
Yeah. Now, what is the strain along normal strain along AC, diagonal AC? What will be the normal strain here? What is the final dimension is AC dash minus what is the initial dimension is AC whole divided by initial dimension is AC. Now here you can see that, but AC is equal to what? AP, right? AC is equal to AP. Now substitute AC is equal to wherever AC is there. Here in the numerator only you substitute here. AC is equal to AP in the numerator only. Now AC dash minus AP divided by AC. Now what is AC dash minus AP? That become what? C dash P or P dash P C dash. Now called as equation number 1. Now epsilon AC is equal to P C dash divided by AC, called as equation number 1. Whether we know the P C dash, that is also unknown. Whether we know the AC, the diagonal, that is also unknown. Make it 2 unknowns here. Now first we'll go for determine P C dash. Now how do you determine P C dash? By considering a right angle triangle C dash CP. The included angle is 45 degree. Now if you consider C dash CP, okay, that right angle triangle. Now I need, this is the angle C is 45 degree means, now this is the opposite side, this is the adjacent side, this is the hypotenuse, right? Now consider C dash CP is a right angle triangle. See the consider right angle triangle C dash CP. Now I need which one I need? P C dash, right? Now from this, which angle I want to operate? Trigonometric relation is a sin 45 degree. Sin 45 degree is what? Sin theta is equal to opposite by hypotenuse. Now consider here right angle triangle C dash CP, angle is 45 degree. The side which is opposite to the angle is opposite side. The side which is adjacent to the angle is adjacent side, and one more is hypotenuse side. Now opposite side is P C dash, hypotenuse is C C dash. Right? From this, what is our aim? Our aim is to calculate P C dash. P C dash is equal to sin 45 degree into C C dash. Sin 45, as you know that trigonometric relation here, sin 45 degree is 1 by square root 2. Now called as equation 2. This is first term we determined here. P C dash is 1 P C dash is 1 over by square root C C dash. Again here C C dash is unknown. We don't know what C C dash in the known parameter. Then how do you determine C C dash? Again we consider one more right angle triangle C dash C and D. C dash C and D. We consider one more right angle triangle. Then you apply here. What angle you want to apply here? This angle here included is gamma. Right? The side which is opposite to gamma is, this is the opposite side. C dash C is opposite side. The side which is adjacent to the angle gamma, it is CD, that is adjacent side, and C dash D is hypotenuse. Now I need C dash, right? Then you go for apply a tan gamma. Tan theta is equal to opposite by adjacent. Right here gamma it is. Tan gamma is equal to opposite by adjacent. What is opposite here? From the right angle triangle C dash C D, it is opposite side is C dash C. Adjacent side is CD. For small angle of theta or small angle of gamma, sin gamma become what? Gamma. Cos gamma means sin 0 is 0, cos 0 is 1, tan 0 is 0. Similarly, for small angle of gamma, tan gamma become what? Gamma. Now instead of tan gamma it is gamma it is. Now C dash divided by CD. From this our aim is to determine what? C dash in the equation 2. That is the aim here. C dash is equal to CD into gamma. Now substitute equation 3 into equation 2. Now finally P C dash is equal to 1 over by square root CD into gamma. Again, CD is also unknown here, right? But for a square lamina, as you know that AB, BC, CD, AD, those are all sides are equal, right? Now CD also we know that because it's a square lamina. So in the equation 1, PC dash we determined. Now what about AC? Again, AC is a diagonal for a square lamina AB, ABCD, right? Now how do you determine AC? Again, we consider a right angle triangle ADC, then you apply a Pythagoras theorem. See that AC you can determine by considering the right angle triangle ADC, apply the Pythagoras theorem. What is the Pythagoras theorem? Says that the square of hypotenuse side is equal to the sum of the square of two adjacent sides. That is AC square is equal to AD square plus DC square. Now as you know that AB is equal to BC, BC is equal to CD, CD is equal to DA. Now we can take it as DC, CD is equal to AD. Now AD square plus AD square will get 2 times of AD square. Now finally AC is equal to what? Square root of 2 into AD. That is the equation number 5. Now substitute equation number 4 and 5 into equation number 1. Now see then the right side here. Now substitute equation 5 and 4 into equation 1. Now epsilon AC is equal to PC dash by AC. What is PC dash? That is the equation number 4. 1 over by square root into CD into gamma whole divided by what is equation number 5? That is AC. AC is equal to square root of 2 into AD. Now AD CD get cancelled because of AD is equal to AB is equal to BC, BC is equal to CD, CD is equal to DA. Means AD is equal to CD. Those two get cancelled. See that CD get cancelled. Finally, what do you get? 1 over by square root divided by square root become 2. Here, right in one more term here, gamma. Now, this is a very, very important equation, equation number 6. Now, the strain, normal strain along the diagonal or normal strain is always half of the shear strain. Now, remember this equation. Now, see the statement here. Normal strain is always half of the shear strain. That we get from the equation 6. But what is our ultimate aim? Our aim is to determine the relation between Young's modulus and shear modulus. But here I got the relation between the strain along the normal strain and shear strain. Then how do you determine those relation? Again, you go for apply a generalized Hooke's law. That's why we discussed generalized Hooke's law in the so few minutes earlier. Why we discussed here now comes to know that. Now equation 6 says that normal strain is half of the shear strain. Okay, after that I want to determine the relation between Young's modulus and shear modulus. Now again consider the same square lamina. See the same square lamina. It is normal strain takes place along the diagonal. If I make it along the diagonal, see that AC become AC dash. For that, we'll consider a small element, a small cube inside the lamina also. Now, if AC is increases means along that direction, what type of stress acting here? Normal stress is acting. Sigma 1 is acting. Tensile stress is acting along the AC direction. AC or AC dash. At the same time, see that B, D and B dash, B dash and D, those two corners are nearer each other. Means a compressive stress is acting on along the diagonal BD, right? Now that is sigma 1 is acting along the AC, sigma 2 is acting along the BD diagonal. Then those stresses are equal. Sigma 1 is equal to sigma 2 and also that is equal to what? Tau, shear stress. Now consider an element oriented along diagonal AC and BD is subjected to tensile stress sigma 1 and compressive stress sigma 2. The magnitude of these normal stresses is equal to shear stress. Sigma 1 is equal to sigma 2 that is equal to tau. Now we'll go for apply. Now consider this is a element subjected to two stresses. One is tensile stress, another one is compressive stress. Right? We'll consider only the two-dimensional object. If it's three-dimensional means sigma 3 also will come to the picture. But here we consider only a lamina, square lamina. Now apply the generalized Hooke's law on the element. What is the generalized Hooke's law? The strain induced along AC that is equal to See that along AC, sigma 1 is there. Is a tensile actually, it is not compressive, tensile. Stress sigma 1 is tensile nature, sigma 1 by E. Now along another direction, BD it is compressive, right? That's why negative, sorry, what is generalized Uxla said that the strain induced along the direction is equal to sigma x by E minus mu times sigma y by E minus mu times sigma z by E, right? But here z direction is not there, only x and y direction is there. Now sigma AC is equal to sigma 1 by E minus mu times of sigma 2 by E. Again sigma 2 it is in what in nature? Compressive nature. That is why we get minus sign here. Minus sign here. Yeah, now the next slide is visible. Yes, next slide is
Yes, sir.
visible. Yeah,
Yes,
now
sir.
minus into minus become plus here. Minus of sigma 2 here minus and become plus. Now what is sigma epsilon AC is equal to sigma 1 divided by E plus mu times sigma 2 by E. Now as you know the sigma 1 is equal to sigma 2 is equal to tau. Now substitute sigma 1 is equal to tau, sigma 2 is also equal to tau. Now take the common term, tau by E is the common. Now we'll get 1 plus mu. Now this is the what is the strain induced along the diagonal AC. Epsilon AC is equal to tau by E into 1 plus mu. That is called as equation number 6. Now compare equation 6 and 7. What is the equation 6? See, the equation 6 is the normal strain is always half of the shear strain. That is the equation 6. What is the equation 7? Equation 7 shows the normal strain along the diagonal is tau by E into 1 plus mu. Now compare those two equations. Left hand side are also equal, right hand side also equal of those equations. Now gamma by 2 tau by E terms of 1 plus mu. Now rearrange the term. See, the send the E to the left side, gamma and 2 to the right side. Now E is equal to 2 into tau by gamma 1 plus mu. What is tau by gamma? Tau stands for what? Shear stress. Gamma stands for shear strain. The ratio of shear stress to the shear strain is what? Shear modulus. Now what is the equation we get? Relation between Young's modulus and shear modulus is Young's modulus E is equal to 2 times of G into 1 plus mu. Now this is the relation between Young's modulus and shear modulus. Or you can rearrange the term. G is equal to E all divided by 2 times of 1 plus mu. Any one formula you can remember. Better you go for remember the first method, first formula. E is equal to always Young's modulus is a double of shear modulus into 1 plus of gamma. Gamma is nothing but what? Poisson ratio. And from this equation, what is the information we will get? Young's modulus is always greater than shear modulus. Now this is the relation between Young's modulus and shear modulus. Now how do we derive that equation? First you consider a square lamina of equal sides, then a shear force is acting on that lamina. Now we will go for express what is the strain induced, normal strain induced along the diagonal AC is equal to half of the shear strain induced in the lamina. That is the first step. Second step, we will apply generalized Hooke's law. As you know, generalized Hooke's law is the strain along that direction. Epsilon x is equal to sigma x by E minus mu times of sigma y by E minus mu times of sigma z by E. But here we consider only a square lamina. Here we consider only a square lamina. That's why the strain along the z direction is, stress along the z direction is 0. That's why we'll get only 2 terms here. Okay, in the strain along that AC will get only 2 terms. Now we apply generalized Hooke's law, then compare those two equations. Finally, we will get the relation between Young's modulus and shear modulus. Now you should remember this formula also. Yes, any doubt regarding this derivation? So try to solve, try to derive it. If you not able to derive, if you not able to understand means when you comes to an offline for regular class, again we will go for discuss in what we call as a short term courses we will do, then you can understand it. Okay. Yes, any doubt? Okay, next one is relationship between Young's modulus and bulk modulus. Again, this what you call derivation you have in your syllabus. You should remember this one. Directly they will not given the relationship between Young's modulus and bulk modulus. They given volumetric strain and volumetric stress. That term is given. Okay. Now those two terms will come in this derivation. Now here the relationship between Young's modulus and bulk modulus. Now again we will consider a cube. See that cube here figure of size how much? A in the length, width also A, height also A. All sides of the cube are same. Its size is A. The what is the volume? Initial volume of the cube is A into A into A cube. Right? Consider a cube of side A which is subjected to spherical stresses. The initial volume of cube is A cube. Spherical stresses means the stresses are acting all three mutually perpendicular direction. The stresses are acting on three mutually perpendicular stresses but acting in same magnitude. This magnitude should be same. Then those stresses are called as spherical stresses. The normal stresses acting in all the three mutually perpendicular direction of same magnitude. Those stresses are called as spherical stresses, right? Now initial volume of the cube is A cube. Now once the cube is subjected to a spherical stresses, all the three direction a sigma is acting. What happens once all the directions sigma is acting along x-axis, y-axis, z-axis, all the direction sigma is acting, normal stress acting means volume increases. It increases its volume. When the element is subjected to spherical stress, then the final length of the each side of the cube is A is the initial length. Now it increases A to A plus delta A. Increase in length here, increase in dimension delta A. Now what is the final volume of the element is A plus delta A into A plus delta A into A plus delta A, that become A plus delta A whole cube. Now initial volume of the cube is before applying spherical stress A cube. Once you apply spherical stress on the cube, what is the final volume of the cube is A plus delta A whole cube it is. Now from this what type of strain will get? Now this slide is visible.
Yes, sir.
Yeah. Now what type of strain will get here? All the three side the same stress is acting in all the three mutually perpendicular stresses acting in same magnitude, acting along those coordinate axes. Now volume increases. Means what type of strain will get? Volumetric strain. Right? Now volumetric strain is defined as is a change in volume to the original volume. Now what is the change in volume? In the numerator you can see that final volume minus initial volume. What is the original volume? In nothing but initial volume. What is the final volume? As you know, the final volume is A plus delta A whole cube minus what is the initial volume? A cube whole divided by what is the initial volume is A cube. Now expand this term numerator A plus delta A whole cube. How do you expand here? A plus B whole cube formula. What is A plus B whole cube formula? A cube plus B cube plus 3AB into A plus B. Now we'll go for expand this numerator term. Right? See that epsilon V is equal to A cube plus delta A whole cube plus 3A into delta A plus delta A minus A cube divided by A cube plus A cube minus A cube get cancelled. Now finally we get this term. Again we will go for delta A is very small element. Delta A square or delta A cube become very small. Delta A is small means suppose assume delta A is 0.001. Now multiply 0.001 into 0.001 becomes 0.1 into 10 to the power of minus 4 or minus 5 will get. Means very small. Delta A is small. Delta A square and delta A cube is become very small. Then we will go for neglect those term. Where delta A is small value, then delta A square and delta A cube are become very small. Hence neglect the higher order term. Now finally what we want to neglect these two terms, finally epsilon V is equal to 3A square into delta A whole divided by A cube. Now A square, A cube, those two get cancelled, finally you get new denominator only A. Now epsilon V is equal to 3 times of delta A by A. What is delta A? A stands for what? One side length of the volume, one side length of the cube. Now change in length to the original length, that gives what? A normal strain, because all sides are equal, x-axis, y-axis, z-axis. If you take 3 axes, the cube the length of the cube along those axes should be same. That's why you'll get, see that where delta A by A is nothing but what? Normal strain. That is equal to, it may be along x-axis or y-axis or z-axis. Epsilon x is equal to epsilon y, that is equal to epsilon z. This is a very, very important one. Remember this. This again we'll go for use that, derive the equation. Now finally what you get? Volumetric strain is 3 times of a linear strain. That is equal to, what is the linear strain? You can say that epsilon plus epsilon plus epsilon. That is equal to 3 times of epsilon. Now epsilon is substitute here. One is epsilon x, another one is epsilon y, another one is epsilon z. Now we'll get epsilon x plus epsilon y plus epsilon z. Now called as equation number 1. And also here from this linear strain is equal to, it's a volumetric strain divided by 3. Volumetric strain divided by 3. Now by applying generalized Hooke's law, now up to this we determine only the cube is subjected to a volumetric stress. What will be the strain induced here? Then we go for apply the generalized Hooke's law. What is generalized Hooke's law? As you know that the strain along x direction is equal to sigma x by E minus, here instead of nu they use mu. Both are same. As you know that Poisson ratio we can represent either nu or mu, but here the student has taken mu here. Okay, so minus nu into sigma y by E minus nu into sigma z by E. This is the generalized Hooke's law along x-axis, right? Now see that. Now what is the stress acting in x-axis, y-axis, z-axis? All these 3 coordinates. What are the stresses are acting in x-axis is sigma, that is sigma x. Y-axis also sigma. Z direction also sigma is acting, right? Now stresses acting in all those direction here. Sigma x is equal to sigma y is equal to sigma z. That is equal to sigma. That is equal to sigma s. Sigma suffix s. Now substitute here. Now take the common term. This is the common term here. Sigma s by E. Take sigma s by E is outside. 1 minus mu minus mu. Minus mu become 2 times of minus mu. Sorry, minus 2 times of mu. Now this is a relation between the linear strain along the spherical stress, called as equation number 3. Now compare equation 2 and 3. Left hand side are equal. Equation 2 is linear strain is 1/3 of volumetric strain. Equation 3 is linear strain is in terms of spherical stress it is. Now when you compare equation 2 and 3, now you simplify it. Okay. Well, how do you simplify? Send this E to the left side, then epsilon by 3 to the right side. Now finally we'll get Young's modulus is equal to 3 times of k into 1 minus 2 times of mu. Again see that Young's modulus is always again greater than bulk modulus. 1 minus 2 times of mu value is varies from 0.25 to 0.35 for engineering material. If you substitute this value, that will not much varies here, means half of it, right? Okay, now Young's modulus is greater than bulk modulus. Again remember this relation. E is equal to 3 times of k times of 1 minus 2 times of mu, or bulk modulus in terms of Young's modulus also you can remember it, but any one formula you should remember. Okay. Now this is a relation between Young's modulus and bulk modulus. Again this is your important equation for your syllabus. This content is there. Volumetric strain and volumetric stress. That heading is there. You can check in your the syllabus. Right? Yes. Any doubt regarding this derivation? Again here also in this derivation, first you go for relation between Young's modulus and bulk modulus. First you consider the bulk modulus related object, that is a cube. When it is subject to spherical stress, what is the strain induced in the cube? That we express in terms of linear strain. Then you go for apply a generalized Hooke's law. Then you go for compare those two equations. Finally get the relation. This is the approach. How do you go for derive the equation? Don't simply by heart or don't simply go for by heart or remember it. You go for use the logics. How do you go for, why do you go for derive it, and how do you go for derive it? What the concept behind that? Okay. Yes, any doubt? Yes, students? Yes, my voice is audible?
Yes, sir.
Okay.
Yes, sir.
Now today I'll go for one more derivation. This is the last derivation for this session. Okay, this is a simple one also. It is, see that in the first derivation, relationship between Young's modulus and shear modulus. What is the relation between Young's modulus and shear modulus is E is equal to 2 times of G into 1 plus nu or mu it can take here. Second derivation what we have studied here, relation between Young's modulus and bulk modulus, that is E is equal to 3 times of K into 1 minus 2 times of mu. But here in the third derivation, relationship between Young's modulus, shear modulus and bulk modulus, E, G, K and also mu, okay, or E, G and K. For all the elastic constant you can easily, what is the relation between there, right? Now we know the relation between Young's modulus and shear modulus, that called as equation number 1, and relation between Young's modulus and bulk modulus you can call it as equation number 2. Now we'll go for compare these two equations. Why do you compare here? Left hand side is Young's modulus only. Young's modulus term is there. Then you go for compare equation 1 and 2. When you go for compare 1 and 2 equation, now this is a 2 times of G into 1 plus mu is equal to 3 times of K, 1 minus 2 times of mu. Now expand this equation. Send 2G inside the bracket, send 3K inside the bracket on right left hand side and right hand side. Now see the here, when you simplify it, now again rearrange the term, take the constant outside. Finally you get mu is equal to 3 times of K minus 2 times of G whole divided by 6 times of K plus 2G. Now substitute equation 3 into either equation 1 or 2. Substitute equation 3 into the equation 1 or 2. Then you go for simplify it. Once you go for simplified, finally what you will get? Young's modulus is equal to 9 times of Kg divided by 3 times of K plus G. Now, before starting this session, I told you that for engineering material, for isotropic, we just give two elastic constant. One is Young's modulus, another one is Poisson ratio. Then how do you determine the remaining two? The elastic constant here, you can see that equation 1 is E is equal to 2G into 1 plus mu. Now you substitute E value, if you substitute mu value, you can easily determine what is the shear modulus for the material. Next, second equation you can see here, if I know the Young's modulus and Poisson ratio, substitute into the equation number 2, you can easily find what will be the bulk modulus of the material. Now, if I want to make it relation between Young's modulus, shear modulus and bulk modulus, then you go for, see the Young's modulus is equal to 9 times of Kg divided by 3 times of K plus G. These are the derivation, out of which you can expect one derivation. You can check the previous year question paper for your 1 or 2, once they ask this question, relation between the Young's modulus and bulk modulus, or Young's modulus and shear modulus. You can check the previous year question paper. Okay, today in the last topic, so up to what we studied, that you'll go for solve the problem. Okay, now remember again in the list of formula, write those three formulas. One is relation between Young's modulus and shear modulus. Second one is relation between Young's modulus and bulk modulus, and third one is relation between Young's modulus, bulk modulus and shear modulus. Okay, in the list of formula you should write down. Yeah. After that, now you take notebook, calculator, pen. Yes, take 2 minutes time. Take notebook, calculator and pen. Yes, all of you have those things. Shall I continue? Okay, I will take only maximum 5 minutes. I will wind up this class. Yes, give me response.
Okay, sir.
Yes, sir.
Okay, sir.
Yeah. Now see the problem. when a 12 mm diameter specimen is subjected to a tensile force of 20 kilonewton. On deformation of 0.3 mm is observed over a gauge length of 150 mm. Reduction in diameter, pi stands for what? Diameter. Reduction in diameter is 0.0079 mm. Determine first one Young's modulus, second one Poisson ratio, third one shear modulus, and fourth one is bulk modulus. Yes. Read the problem once or twice, then write the appropriate sketch. Already I have shown here. Write the appropriate sketch and also write the given data. If you have unit conversion, then go for unit conversion. See that when a 12 mm diameter specimen, now this what type of specimen it is? Circular cross section specimen. How much diameter it is? 12 mm. D is given. A 12 mm diameter specimen is subjected to what load? Tensile load. How much here? 20 kilonewton. You take a tensile load, either it may be P or F. Here is consider the notation is F, or you can take P also, no problem. After once you apply 20 kilonewton load on the 12 mm diameter specimen, the deformation of 0.3 mm is observed over a gauge length of 150 mm. This is the length of the specimen. Over the 150 mm length of the specimen, deformation is induced. That is how much? 0.3 mm. So what it indicates here? Change in length of the specimen, delta L. Delta L is equal to 0.3 mm over a gauge length. L is equal to 150 mm. Now reduction in diameter. Once 0.3 mm change in dimension takes place along the length, at the same time what happened? Diameter is reduces from 12 mm to what? Reduces. How much reduction here? 0.07 mm means delta D it is, not the D2, it is delta D. Reduction in 0.079 mm. Determine Young's modulus, Poisson ratio, bulk shear modulus and bulk modulus. Now take the problem, write the appropriate sketch. Now write the given data, then go for determine here. Now tell me the value of E. So geometrical property is given, diameter is given, length is given, then loading property is also given, that is 20 kilonewton. After that, once you apply load, what happens? The diameter is, length is increases, diameter decreases. Then how to calculate Young's modulus? How to calculate Young's modulus? There are two approaches are there. One is, because this rod is made up of uniform cross section, you can apply delta L is equal to PL by AE. One formula you can directly apply. Or, as you know that you apply the Hooke's law. What is Hooke's law? Sigma is equal to E into epsilon. First you calculate sigma. Sigma is equal to what? P by A. Epsilon is nothing but change in length by original length. Then you substitute back here. Now you get the E value. Now tell me what is the E value? Now we'll check who will tell the first. Again, it is circular cross section. Other dimension, if you want cross sectional area, pi by 4 d square, right? Yes, anybody got the value? Young's modulus? Okay, take 3 minutes time, complete all the calculation and tell me the answer. Yes, anybody got the answer?
88.4 kilonewton
88.4
into 10
into
power 3
square of 3
Newton meter.
Newton per mm square. Be careful
Millimeter
about the
square.
units, right? Yeah, good, Grishma. Next, Poisson ratio. How do you determine Poisson ratio? As you know that it's the ratio of lateral strain divided by longitudinal strain. Lateral strain nothing but what? Change in lateral dimension. That is the delta D by D. Longitudinal strain is nothing but change in length by horizontal line. Now you substitute, you will get mu value. Now once you get mu value, you check for engineering material what should be the Poisson ratio. It varies from 0.25 to 0.35. Whenever you get the answer, please verify whether your answer is right or wrong. How do you check? We'll compare with some other way, right? Yeah, Poisson ratio, you should get the value in between 0.25 to 0.35. Yes, who will tell that answer? Now who will give the first answer for that?
0.32.
0. Yes?
32.
Yeah, 32. Lahari, right?
Yes, sir.
Good, ma'am. Next, shear modulus. How do you get shear modulus? If you already calculate Young's modulus, if you already know the Poisson ratio, we know the relation between the Young's modulus and shear modulus. E is equal to 2 times of G into 1 plus mu or 1 plus nu. Now substitute that equation, in that we will get G value. Now we will tell that answer for that. Third one, G. Then check, once you get the answer G value, the G value should be less than Young's modulus, or Young's modulus should be greater than shear modulus. Whatever the shear modulus should be less than Young's modulus. Then you check the recheck the answer whether you got the right or wrong. If you more than that means somewhere your calculation is wrong. Yes, what is the G value you got? Itasham? Aradhana?
Yes, sir. Doing, sir.
Yes, Grishma, tell me, what is the answer?
33.26 into 10 power 3 Newton millimeters mm square.
Newton per millimeter square. Okay, be careful about
Yeah.
unit, Grishma. You are telling the
Yeah,
numerical
okay.
value is right, but unit is wrong. Be careful that. Okay, answer is right, Grishma. 33.26 into 10 raised to power of 3 Newton per mm square.
Yeah.
Next, after that, then we go for calculate bulk modulus. How do we calculate bulk modulus? We know the Young's modulus, we know the Poisson ratio, then we know the relation between Young's modulus and bulk modulus. E is equal to 3 times of K, 1 minus 2 times of nu or mu. Again, whatever that bulk modulus value you get, that should be less than Young's modulus. Yes, we will tell the answer for the last one. Kalparaj M. Miramat. Are you there, ma'am? Yes, Rutuja. What is the answer for the last question, ma'am?
Doing, sir.
Still you are doing?
Yes, sir.
Yeah. Janvi?
Sir.
What is the answer for the last question?
Sir, I'm checking, sir.
How much you got, ma'am?
81.86 into 10 power 3 Newton per mm square.
Aradhana, sorry, how much?
81.86 into 10 power 3.
81.86. Any other value? But you are nearer to that exact value, but that is not the exact value. Anybody got other than that 81 point? Something?
86.17
Yeah.
into 10 power 3 nmm
Ah.
square. Newton square.
Yes, good Vishma. 86.17 into 10 raised to the power of 3 Newton per mm square. Yes, do this calculation. Okay. Yes. Yes, anybody got same answer? All of you got the same answer or any other different answer you got? Yes, Aradhana, you check in substitution and also check in while doing the calculator, check the input values. Okay?
Okay, sir.
Yes. Yeah, up to this it's discussed here. In next class, we'll we'll take the one more topic. Okay, I think the slide is visible. Yes, someone has to give the response. Slide is visible.
Yes, sir. Yes, sir.
Yeah, the problem
sir.
is solved here. What is the value of? Yeah, Young's modulus 88.415 10 raised to the power of the Newton per mm square. Mu value 0.329. And shear modulus 33.26 into 10 raised to the power of the Newton per mm square. See, the shear modulus is less than Young's modulus. Again, bulk modulus is 86.17 into 10 raised to the power of the Newton per mm square. That also should be less than Young's modulus. Whenever you go for solve the problems, once you get the answer, check whether the answer is right or wrong. Okay. Now next class we'll go for study the one more topic is thermostresses. Okay, next class I think yeah, Tuesday, Wednesday we'll do the class, right? Yeah. So until that you try to solve the question paper problem. Okay, those are the assignments. So what are the assignments you have to consider here? You solve the question paper problem. I think I already sent the question papers into your WhatsApp group. You take the assignment, you write in A4 sheet only. Okay, what are the problems is what we covered here. Same related problem if you appeared in the question paper, write down those, take that as an assignment and take the question and solve it. If you have doubts, you contact to my number. Okay. Yes. Thank you guys. Thank you for attending the class. So we'll meet on next Wednesday, right? If you have any doubt, you can ask me or else I'll end up this session. Any doubts are there?
No, sir.
Aniket Arai. Okay, ma. Okay, just I'm leaving the session. Yes, thank you for attending the session. I will end this meeting. Thank you, one and all.